Oh, my name is John Ensworth, and I'm just the opening act. I just do a little new Astro News update each month to get you guys worked up for the actual main event here. So this month's update will be a SETI update. Who knows what SETI is? Okay, say it. All together. No, very good. So we just had a release from the Listen Breakthrough project. They've now looked at, for a little while, the 1,327 stars in the beginning of their planned 10-year mission to individually look for radio signals and other signals from these stars. Now, the first time we looked was Project OZMA, I think that's how you pronounce that, in 1960, run by Frank Drake at Cornell. Russian billionaire Yuri Milner has put a bunch of money behind this, $100 million, to really look for signs of life out in the universe. So this new initiative, funded by Yuri, began in 2015. It uses the Green Bank telescope in West Virginia, the Parkes telescope in Australia, and the automated planet finder in California at Lick Observatory. And in the next phase, they're going to bring in the Meerkat array in South Africa. They just did this release that they have collected their first petabyte of data, 1 million gigabytes, and they have not found anything yet. Hi, everybody, we haven't found anything. I mean, that's a lot of data right there. I mean, this is a lot more than Netflix pumps out, I think, but just by a little bit. The Green Bank telescope here is looking at, in specifics here, 43 stars, all within 5 parsecs. It's about 17, 18 light years from us. It's looking at 1,000 stars of all spectral types within 50 parsecs. So multiply by 3, it's about 160, 150 light years. 1 million nearby stars. Look at the center regions of our galaxy and 100 nearby galaxies. And they're looking at a few interesting things like 20 white dwarfs, 20 neutron stars, and 20 black hole environments, just to see if maybe someone's got a data center parked around a black hole for some reason. Who knows? The Parkes radio telescope is covering the southern hemisphere from 1 to 4 gigahertz and the galactic plane in the center of our galaxy. And the automatic planet finder is going to kind of look at these same things that the Green Bank is, but looking at the visual part, looking for pulses of laser light. And I'm going to talk about more in the second little part of the update here. Optical SETI. So yeah, radio astronomy is a great way to look for television, radio, shortwave, cell phones, all the radar things that civilization might pump out by accident. If anybody saw Contact, there's a sphere of television going out where I Love Lucy is now being seen 45 light years out, I think. So, and of course in that movie, the first radio signal is the first Olympic transmission that television transmission for the Olympics that had a very controversial image. No spoilers of the movie. But what they're doing with the automated planet finder is looking for laser pulses, because we're trying to get more information into information conduits all the time, and radio is kind of slow and kind of clunky. So we're using laser light in optical circuitry, so laser is a great way to do communication. So this is a 2.4 meter telescope, first built in August 2013. It is looking for extrasolar planets, which you might hear more about tonight. But it's also working with the Breakthrough Listen project, looking for laser pulses from extraterrestrials. So the idea is that a Titanic laser could be pointed this direction, not this thing. This is not going to do it. It would even outshine the sun of the planetary system that it's in. It could be. very, very big. Million watt laser. So, a million watts. Yeah, yeah. Oh, that'd be bad. My laser hit an iceberg. These could be microsecond flashes, and we'd have to be right down the path of the laser beam to see it, but it could be detected. And the optical part of SETI began in around the year 2000. The new goal for Optical SETI, that is a big story on the SETI site, is they want to take a picture of the entire observable sky every nanosecond. That's the goal. And so they're planning to do something called PanoSETI. They're going to have geodesic domes with up to 100 hexagonal shaped modules. They each consist of a telescopic lens, a Fresnel lens that is then focusing that down onto CCDs, just like your digital camera, your cell phone works with. Looking at everything above about 30 degrees of the horizon at that time resolution. The amount of data this would generate just dwarfs my imagination. I can't even think of it. No. And this is be looking in the optical and the infrared portions of the visible the electromagnetic spectrum, and they expect to get the first units working within about 2 years. Now, it won't be this whole big system, but that's the goal. So here's a laser coming out of some other planet towards us saying, here is everybody's credit card numbers from alien civilization. How much have we looked at? Should we be discouraged that a petabyte of data shows nothing? Well, one of the SETI astronomers says that looking at all the ways that we could look for conversations and data from other civilizations across all frequencies and time scales, we have about a hot tub worth of water out of all the oceans on the Earth. So there's a lot of job security there. And you can help. You can download the BOINC screensaver, and you can run SETI at home, setiathome.berkeley.edu. And when your computer isn't balancing your checkbook or giving off your credit card numbers to scammers, it can be looking for signals from space. All right. That's any questions on looking for life? Yes?
You said every nanosecond they want to take an image?
Yes.
Are there CCDs that have that kind of?
I don't think so. Not now. No. That's.
You have to have an array to do that, wouldn't you?
Right. It just boggles my mind. I mean, what, petabytes an hour? I just don't know. Yeah.
Where do they plan to put those?
First one's going to be in California, but that could be just, it's convenient to where they're setting things up, and it's proof of concept probably. Right, near the hot tub. Yeah, definitely near the hot tub.
What's the resolution of the all-sky scan?
I don't know that. That's a good question. I mean, you're talking really little pinpoints you need to examine, so. Yeah. Yeah.
Well, we have 1 petabyte so far of information.
1 petabyte down since 1960.
And they're still using screensavers to try and figure out that 1 petabyte.
Yep.
And they want to do that every nanosecond.
I know.
A little ambitious.
It just completely boggles my mind, but that's from the SETI site. That's what the SETI folks want to do. All right, so we're going to do a little tech. Yep. We're switching over now to tonight's main speaker. This is Dustin Putnam from Ball Aerospace, right nearby in Boulder. He had to deal with the traffic on the diagonal to get here tonight, so everybody be really nice to him. He went to work on the Kepler mission, which you're going to hear about tonight. The Kepler Space Telescope search for exoplanets. And he began in 2004 until the mission ended, and now he's doing even more cool stuff that he'll tell you about. So give us a moment while we change over and get him going. Go.
Sorry. Can everybody hear me? Okay, good.
This fight's everybody.
Okay.
I think that's quite there, yeah.
All right. I'm all dressed up now. Okay. And I'm ready. All right. Well, welcome everybody. Thanks for coming. My name's Dustin Putnam. I'm going to be talking about the Kepler Space Telescope and the search for exoplanets. One of the neat things about this space telescope is that it's very local. The telescope and spacecraft was all constructed right here in Colorado in Boulder at Ball Aerospace, which is just down the road. So that gives us a very special connection to this telescope and some of its very remarkable findings that it's given us over the years. And so I'm going to talk about the search for exoplanets and how do astronomers look for exoplanets. But the first question is, well, what are exoplanets? So an exoplanet is any planet that circles a star besides the sun. So any planet outside of our solar system. So these planets have been with us in popular culture for a long time. For actually the first exoplanets were hypothesized by an Italian astronomer by the name of Bruno in the 16th century. So he looked up at the sky and he said, well, there's innumerable stars, so there must be innumerable planets. But thinking that there's something that is out there and knowing that something is out there is really the difference between just thinking something and having an actual science. But moving forward a little bit from that, I have some of our more popular exoplanets from our popular culture. So this is the, can anybody name this exoplanet? Krypton. Krypton, yes. And this one, this is the planet Vulcan, and this is, nope. No, Earth's not an exoplanet. So this is the jungle moon of Pandora, all right, from the movie Avatar with the big blue cat people. So, we've had these exoplanets in our popular culture for a long time, and it just makes sense that if there's a lot of planets around our star, why wouldn't there be planets around all other stars? But we didn't actually know about other exoplanets until the first ones were discovered in 1995. So just 25 years ago. So the science of exoplanets is a very new field, and there's a lot of discoveries happening in it, and it's evolving rather quickly. But exactly why is it that we're looking for exoplanets? Well, one of the questions that we want to answer with the search for exoplanets is, are we alone in the universe? Right? And so are there extraterrestrials somewhere else? And so if there are these extraterrestrials someplace else in the universe, they have to have planets to live on, obviously. So in 1960, an astronomer by the name of Frank Drake formulated this simple equation to come up with to estimate the number of civilizations in our galaxy. And so it starts over here on the left-hand side with things that are known. So this is like the formation rate of stars in our galaxy. And as you move towards the right-hand side, these are the things that are less and less known. So this is like the number of the fraction of those stars with planets. And then this is the fraction of those, the number of Earth-like planets around each one of those stars that has planets. And so you add up you multiply all these things together, and they give you the number of civilizations that are in the galaxy currently. So most of these stuff on the right-hand side we don't know of. And so one of the questions that Kepler was trying to answer was this parameter here. Of all the stars in the galaxy, how many of those have planets? So if not very many of those stars have planets, well then it's less likely that there are ETs out there. But if every star in the galaxy has planets, then there's much more places for ET to grow up and mature and turn into a technological civilization like ours. So that's basically why we're looking and how we're looking. So we want to look for planets around other stars. So how do we do that? Stars are big and they're bright, and planets are small and dim. But we have big telescopes. So if we take a big telescope and we look at other stars, can we see planets circling around other stars? Just like Galileo did with his telescope back in 1610 when he looked at Jupiter and he saw the moons of Jupiter going around it. You should be able to see planets orbiting other stars. Well, that is one method to finding planets around other stars. The problem is exactly what I was saying before, is that stars are so bright that they really outshine their planets. Planets only shine by reflecting the light of their stars, and they only reflect a very small percentage of that light. About 1 part in a billion of that light that those stars are producing actually gets reflected by those planets. So it's really hard to find planets with that method. So astronomers started looking for other methods of finding planets around other stars. One of these things is called astrometry. So as the planet goes around the star also orbits a common center of gravity of that system. And so if you can monitor stars really closely, you can see this subtle tugging, this subtle motion back and forth of that star as the planet goes around. The issue with this method, though, is that it requires really exquisitely fine measurements of those angles of how that star is getting deflected. Because stars are big and planets are small, those stars aren't moving around, aren't moving back and forth very much. But there's a second method that astronomers have used that has been more successful, and that is called the Wobble Method. And so instead of looking for the actual displacement of this star, it's looking for that star's motion towards or away from us. And so the way that works is that you can see that that star is moving around that common center of gravity, but then if it's close to our line of sight, then it's also moving both towards us, and you can see the light getting bluer, and then as it starts to move away from us, that light starts to get redder. So you're basically looking for that velocity signal of that star as it's moving around that common center of gravity. But again, this is these are very small signals that we're looking for. So as you can imagine, the amount that star is moving is proportional to the ratio of masses. And stars are very massive and planets are very small. But if you get smaller stars, you can see smaller planets. And so if you get a star that's very small, about 1/10 the mass of the sun, and this planet that's the size of the Earth, then the size of the signal that you're looking for is about 1 meter per second. So that's the velocity that you're looking for. So if you compare that, though, to the speed of light, which is 300 million meters per second, again, you're looking for a very small signal. So if you're looking for the signal of me walking across the stage, and comparing that to the speed of light, there's a huge difference there. That's again another part, 1 part in a billion that you're really looking for. So there's this fourth method of looking for stars called the transit method. And so what that is that as that planet is moving around the star, if the alignment of its orbit is just right, as that planet goes in front of the star, the light from the star will dim suddenly as the planet goes in front of it, sort of like a mini eclipse. And the benefit of this method is that the sensitivity that the methods need is much less. So basically, if you're looking at the sun and you're comparing that to the sizes of the planets, then if you're looking for a Jupiter-sized planet, Jupiter blocks about 1% of the light from the sun, so as viewed from a distant observer. So you're looking for a change in brightness of about 1 in 100. So if you compare that 1 in 100 to 1 in a billion, now you're talking about something that's much more realizable. But we're not just looking for Jupiter-sized planets, we're looking for Earth-sized planets. Earth-sized planets are much smaller. So again, the Earth is about the 10th of the size of Jupiter. So instead of 1% of dimming, you're looking for about 1/100th of a percent of dimming. So 1 part in 10,000. So you're really starting to stretch things a little bit more, but that 1 part in 10,000 is still significantly easier to see than that 1 part in a billion that the other methods are using. The drawback, though, is that the transit method will only observe a very small fraction of the planets just due to random alignment. These solar systems can be oriented randomly with respect to our line of sight. So what you actually need is that plane of those orbits to be aligned with our line of sight. So if you're looking at a star and its planets are going around it like this, you would never see it with the transit method because those planets would never go in front of their stars. But so if you look at, well, what sort of percentage of the stars should we be able to see that have planets? So it has to basically be in this really tight alignment, and this tight alignment in terms of probability depends on how far those planets are from their stars. So close-in planets are easier to see, like Mercury would have about a 1% chance of seeing that. And then as you get down to Earth, you get about 0.5% of seeing that from a distant observer just based on random alignments of orbits. So how do you combat this? So the way to combat this really is to watch a lot of stars. So basically if you take a very large sample of stars and watch them for a very long time, then you'll be able to see, at least you'll have some idea of what if the fraction of those stars actually have planets. So there's other considerations that go into Earth-like planets. You've heard of something called the Goldilocks Zone. So these planets have to be in a particular distance from their stars so that liquid water can exist on their surfaces. So if you take the analogs from our own solar system, so Venus is too close to the sun to be considered Earth-like. All of its water has boiled away. And Mars is too far away. So it's like Goldilocks and the porridges. The porridge is too hot, the porridge is too cold, but for Earth, the porridge is just right. And so every star has this Goldilocks zone, this green zone around it, where Earth-sized planets can retain water over long periods of time. So in order to be considered Earth-like, these planets need to meet certain size and distance requirements. And so when formulating the way to look for these stars and to look for these planets around stars, one of the important characteristics was determined by this guy named Kepler, who was an astronomer in the 17th century, who formulated the 3 laws of planetary motion. And the 3rd law of planetary motion is really the law of planetary motion that the Kepler Space Telescope utilizes. And that is that there is a relationship between the distance between that star and the size of its orbit. And that relationship is fixed for all planets around in our solar system, and it's the same relationship, it's the same basic relationship between the mass of the star and the sizes of those orbits for all other stars. So if you put this together with the other components, and astronomy is kind of like a detective story. You have a bunch of clues, and you have to follow the clues and put all the clues together in order to come up with a complete story. So how do you measure planets with the photometry? So each star has some observed brightness, some observed luminosity. Astronomers have known for about 100 years of the relationships between this luminosity, the mass of that star, and the size of that star. So if you know how bright a star is, you know how massive it is and how it should be tugging on how it should be holding the planets that orbit around it. And once you know that the mass of that star, if you can observe the period and depth of dimming that you get from that transit method when those planets go in front of their stars, there's a depth of dimming, and so that tells you how big the planets are with respect to the sizes of their stars. And you observe how frequently that dimming happens, and that allows you to really work out both the orbital distance the period gives you the orbital distance for that planet, and the depth of dimming tells you the star to planet size ratio. So that really gives us the clues that we need to see, well, is that planet inside the Goldilocks zone? Is it outside of the Goldilocks zone? Is it too big? Is it too small? You know, what size of what size of a planet is it? So we put all these things together to a mission that basically looks at 156,000 stars simultaneously. And it doesn't move, the telescope doesn't move. Because if you think about, if you're a distant astronomer and you're looking at our sun for signs of planets, in order to see the Earth, you'd have to look for an entire year before being able to see it, because it takes 1 year for that planet to go around the sun, for the Earth to go around the sun, and you want to see that dimming happen multiple times to know, in fact, that it's a planet and that's not some sort of feature that star has, like sunspots. So you have to look at this field of view for a long time. So the idea is to basically take a wide field of view, and this is the Kepler field of view, which is in the constellation, in between the constellation Cygni and Lyra, which, if you're familiar with the wall back here, is up here. And so it's kind of a northern constellation. And so this is basically a 10 degree by 10 degree field of view where we observe 150,000 stars for 4 years to look for this periodic dimming to determine whether or not there are stars, there are planets around those stars. And so this is how the Kepler Space Telescope got started. And basically the telescope was the brainchild of this man, Dr. William Barucki, who used to work at NASA Ames out in Mountain View, California. And the Kepler as a mission was proposed to NASA 5 times before it was finally selected. And the reason why it was turned down 4 times was because the selection committees didn't feel that the technology was mature enough to really support this mission to go forward. But through very persistent efforts of technology development and maturing the mission methodology, eventually they got to the point in 2001 where they were able to submit a very mature proposal that the NASA Selection Committee felt had a very good chance of succeeding. And so this is what the Space Telescope would look like on orbit. And the mission design is somewhat unique in terms of other missions, other spacecraft that you might be familiar with. So the Kepler Space Telescope doesn't orbit the Earth. It doesn't fly out to other planets and orbit them. What it does is basically it goes around it's in an orbit around the sun. It's called a heliocentric orbit. And so basically it's in the specific type of orbit that it's in is called a drift-away orbit. So Kepler is put into an orbit around the sun that it completes an orbit once every 372 days. So it basically falls behind the Earth by 1 week per year. So after the first year, after launch, if the Earth is here, the Kepler Space Telescope would be here. And then it falls behind by one week every year. And so since it was launched in 2009, it's about 10 weeks behind, so not quite a full 3 months, but it's a significant distance. So what this allows, putting it in this heliocentric orbit, what that allowed us to do was basically be able to look at this single patch of sky for the full 4 years at a time without ever having to worry about obscuration from the Earth, because spacecraft that orbit close to the Earth have to contend with the fact that there's this really big object that might be blocking the view of the sky, that object being the Earth. And so we were able to look at the same field of view for those 4 years, and then every 90 days, basically what you had to do was turn the telescope 90 degrees because there's only solar panels on one side. So you can think of it like this, that from Kepler's point of view, the sun is moving at about 1 degree per day, and then after about 3 months, the spacecraft has to rotate back those 90 degrees to put the sun back where it started, so then it would then again move across that wide range. And so looking at the guts of the telescope, so it's a very simple telescope. It's actually probably simpler than a lot of the telescopes that you've looked through here. So just light comes in the barrel, and then there's a mirror back in the back end of the telescope, and that focuses the light on the CCDs, the camera array. And so that's it. So it's a very simple design, but it's simple by necessity because it's not focusing on just a small area of the sky. It's focusing on this really wide 10 degree by 10 degree field. And so this is what the actual focal plane, or this is the CCD array that was mounted inside of Kepler. This is a picture that was taken in Boulder in the clean room before it was installed in the rest of the spacecraft. And each one of these modules is about a little more than a 4 megapixel camera. And so that doesn't sound like much today. I mean, this is 12 megapixels, so, but you know, all up, this was a 95 megapixel camera. And so, you know, back when it was proposed and, you know, finally accepted in 2001, that was a really big deal. It's also a big deal because this 95 megapixel camera was going into space. And so all the electronics and all the camera components needed to be space qualified. And so that's a much bigger deal than what goes into your cell phone camera, which doesn't have to be space qualified. It doesn't have to withstand vacuum of space. It doesn't have to withstand extreme temperatures. It doesn't have to withstand radiation. So this, at the time it was launched, this was actually one of the most complex objects ever to be launched in space just because it had so many micro components. But I've pointed out, in addition to all the CCD arrays that collect the science, also housed on this array are these 4 little blue squares. And so these 4 little blue squares that are each at one corner, those are just smaller CCD arrays. And what those are like really small star cameras that the telescope and spacecraft use to lock onto to make sure that its stability, or how well it's pointed, you know, in space to keep that line of sight pointed in the same direction, is really, really exquisite. And so basically, each one of these tiny CCDs looked at a set of 10 stars, and so a total of 40 stars were used to help keep the telescope pointed in the same direction with a great deal of stability. Now, what do I mean by a great deal of stability? So if you think of small angles, you think that 1 degree is a small angle. So you can subdivide 1 degree into smaller measurements of angles. So you can subdivide 1 degree by 60, you get what's called an arc minute. And if you divide each arc minute by 60, you get what's called an arc second. So each arc second, so it takes 3,600 arc seconds to make up a full degree. So the stability of the telescope when it was on orbit was something that was measured in milliarc seconds. So thousandths of an arc second, so millionths of a degree. That's how stable that line of sight was. And the astronomers really needed that level of stability in order to keep those stars fixed on the same points on those cameras to be able to see those small, 1 part in 10,000 signals that they were looking for. And so the spacecraft, had all the normal sorts of components that you would think of. It had solar arrays for power, a high-gain antenna for talking and listening. It had other star sensors on it that were basically wide-field star sensors that let the spacecraft know where it was pointed if it was pointed someplace else besides where they wanted it to be pointed. And these things called reaction wheels. So these reaction wheels are basically just little flat pancake-like devices. There's just a little flywheel inside of it, and you can spin the flywheel. There's a little electric motor that spins the flywheel, can accelerate the flywheel or decelerate the flywheel. And what that does is that produces a torque back on the spacecraft, because through Newton's laws that equal and opposite forces, so if your motors produce a torque on the little wheel inside of this, then it produces an opposite reaction on the spacecraft. So that's a nice way of being able to control the orientation of the spacecraft without having to use thrusters. So it's just using electricity. So what kept the astronomers up at night? So this is obviously an expensive mission. This is a mission that was a long time in coming. So there were certain things that kept the astronomers up at night. One of those was the thermal flexing of the vehicle. So you can think about after the sun goes down, you can sometimes hear your house making little creaking sounds. And so your house is settling. So the same thing was happening with Kepler, because Kepler was fixed in space and had a fixed orientation, but the sun was moving. So if the sun is over here and it's warming up this side of the telescope, and then it's gradually moving over to this side of the telescope is gradually warming up, and this side is gradually cooling down. So that creates this distortion in the telescope that worried astronomers, that made us put the telescope through a lot of testing on the ground. They were also worried about that line of sight jitter that I was talking about. They worried about noisy stars. So if you think about stars, their light curve that they have, if you just look at and measure the brightness of a star, it's not constant. It's actually changing a little bit over time. And that's just due to the fact that stars are like big pots of boiling water. And so there are places on the star that are hotter and rising up, and there's places on the stars that are cooler and sinking down. And so it's like this pot of boiling water, and you get this noise and this measurement from that action. And so that for the sun is a very quiet star. And so its noise is about 10 parts per million, which is only like 1/10 of that signal that they're looking for Earth-sized planets. But for other stars can be noisier, and so they were concerned that other stars might have so much variation in their natural intensity that you wouldn't be able to see those planets transit in front of them. But that's what helped with looking at these stars for a long time, is that you could actually see this dimming happen from planets, and if you see that a lot, it's easier to pick out that signal from the sort of random variation. And the other thing that the astronomers were worried about was this thing called eclipsing binaries. So two stars that are orbiting around each other, and one goes in front of the other. And so that can look a lot like a planet going in front of a star. Now this is what Kepler sees. Kepler sees a bright foreground star, but what's actually back there is there's a bright foreground star, but there are also a bunch of smaller, dimmer background stars. And so if any of these background stars are eclipsing binaries, that can also look like a planet. And so that's something that astronomers were concerned with. And the way to beat that is that there are other methods of analyzing the data that tells you basically whether or not this is a planet or this is an eclipsing, whether or not this might be an eclipsing binary. So we did a lot of very careful testing at Ball Aerospace and a lot of careful assembly to put all these components together, and basically tested things at the component level and started putting everything together. We have a big test chamber up in Boulder. It's called Brutus, and Brutus is this big container that you can pump all the air out, so you can simulate a vacuum and you can make it hot or cold inside of the chamber. And then we actually tested what starlight would look like coming in the barrel of the telescope and then reflecting off of the main mirror and then landing on the camera. And so we did full end-to-end tests to demonstrate that this whole assembly would have the necessary level of accuracy in the determination of how bright something is in order to be able to find these planets, which 1 part in 10,000, or astronomers like to use the parts per million a lot, because it's just easier to relate, because you can talk about different levels of parts per million. So what we're looking for is 100 parts per million, and so they wanted to make sure that they could see signals that were all the way down to like 20 parts per million. And so March 2009, the spacecraft was ready for liftoff. This is a picture of the spacecraft just before it was shipped to Florida. And this is basically the spacecraft development team with all the different subsystems. So personally, I worked on the orientation control system, or it's called the attitude control system of which is how the telescope is oriented in space. And so that was my particular contribution. And so it got into space, and then about a month later, we got the telescope all tuned up, got the spacecraft all tuned up, and started taking images. And so this is basically the first light image from the Kepler Space Telescope. And you can see that there's more stars at this end and less stars at this end. And that was a deliberate choice because if you look too close to the Milky Way, then the density of those stars in the sky, the stars get too close together and it becomes difficult to tell the different stars apart from each other. And so, but then as you get further from the Milky Way, then those stars are further and further apart and you don't have as rich a star field. Like I said, you have to look at a very large sampling of stars in order to see this 1 or 2 chances in 100 of actually seeing the planets that might be around a particular star. So we settled for this middle ground of near the galactic plane, or near the Milky Way, but not in the Milky Way. And we knew right away that we could see planets with the Kepler Space Telescope because they were already existing planets, existing exoplanets that were known, that were going to be in our field of view, that you could test to make sure that the telescope was functioning properly. And so there was this giant planet, there was this Jupiter-sized planet around a star in our field of view that they were able to make early measurements of. And so what were they looking for? Oh, I think my battery's dead. Oh, there we go. So this is the sort of signal that they're looking for, is that there's this noise from the star, and then occasionally you'll see this U-shaped dip in the starlight, and that indicates something is moving in between your line of sight and that star. And so the way the astronomers distinguish these planets from star spots is that as a star spot, as a star rotates, that star spot will come gradually into your field of view. So it has a much more gradual shape to its light curve. So planets will come straight across that disk to start eclipsing that star. So it'll have a very sharp boundary. So what it was is they were looking for that very sharp boundary to distinguish those planets from those star spots. And the telescope is actually so well built that the fine gain sensor that I was using to stabilize the telescope's line of sight was actually, one of them was actually able to see one of these eclipsing events. So there was a while there where I was looking at this data and trying to figure out, well, why is it doing this, when I realized that my sensor had actually found the first eclipsing object with the Kepler Space Telescope. Now, that made the astronomers a little worried at first because they didn't want to be scooped by some guy working on the spacecraft when they had worked on this mission their entire careers. But fortunately for them, not so fortunate for me, fortunately for them, this depth of dimming is about 10%. So that depth of dimming tells you that this object that's going in front of this star is too big to be a planet. So what this actually is one of those eclipsing binaries where you can see two stars that are going around each other. So when you see two stars, you're up at this level of light. When one star goes in front of the other one, it kind of craters down here. And you can see there's sort of a periodic function here where some of the dips are lower than the others. And so that's where one of the stars that's bigger than the other one is going in front of the other one. So you have two different stars of two different sizes, and you can tell that that's what's happening. And also, these stars are so close together that they're actually distorted in their shapes. That they, instead of being perfect spheres, they're actually more of a teardrop shape because you get this sort of peaking here as you're looking at those stars when they're at their maximum separation. You can see more of that surface area. So that's where they're the brightest. And then as they start to rotate towards your line of sight, you see less of that teardrop shape and you see just more of just circular shapes. And so then you get this sort of decrease. So the telescope is really was exquisitely built in terms of its accuracy and its stability. And so some of the very early results from the telescope showed us these other planets, these Jupiter-sized planets that are known as hot Jupiters, because they're so close to their stars that they're much closer to their stars than the Jupiter is in our solar system. Our Jupiter is far enough away that it takes 12 years for it to go around the sun once, whereas these Jupiters take on the order of 3 to 5 days to go around their stars. So these are planets, these are Jupiter-sized planets that are very close to their stars. So that was very encouraging that we could see this. And not only did we see these U-shaped curves, but as those planets would then go around the backsides of their stars, you actually saw a slight increase in the brightening of that star, because then you were actually picking up the starlight plus some of the light reflected from those big Jupiter-sized planets. So you could actually see that subtle little brightening. And what was encouraging was that level of brightening was about the same level of dimming that you would expect from Earth-sized planets. So that was a very encouraging early mission result that later on the telescope was able to demonstrate that with actually finding these Earth-sized planets. And so we started finding these planets around smaller stars. The planets that are orbiting smaller stars generally orbit closer to their stars, and so they go around more frequently, and their habitable zones are therefore much closer. Because those stars are smaller and cooler than the sun, their Goldilocks zone is much closer than it is for our solar system. But these smaller solar systems still had planets of about the right size. So this is a artist rendition of what this planet looks like. So it's important to remember that when you see things on the web or on the news, that when they show pictures of these planets, we don't have pictures of these planets. All these planets are basically some little light curve like this. That's all we see. Is this allows us to determine the basic size of that planet and the size of its orbit, but it doesn't tell us anything about what that planet looks like. Really doesn't even tell us how massive that planet is. It just tells us the size of these planets. But knowing the size of these planets and whether or not they're the right size and whether or not they're the right distance really helps us fill in those gaps as far as exoplanets, how common are planets around other stars, and how common are Earth-like planets around other stars. In fact, Kepler has found planets around a lot of its stars, and it even found planets around a lot of stars where you wouldn't expect to see planets, such as these what's called circumbinary planets. So if you have a pair of stars that are in a close orbit around each other, you can have planets that are in stable orbits around both of those stars. Now, science fiction has given us a lot of examples of different planets around other stars. There's a very popular circumbinary planet from a science fiction movie. Can anybody name that planet? Tatooine, yes. And so Tatooine is a circumbinary planet. And when I give this talk at places like Comic-Con, I get a lot of questions about circumbinary planets because Tatooine was a circumbinary planet. And Kepler found a good number of circumbinary planets. It actually found about 12 circumbinary planets. The problem with the circumbinary planets that they found was that they were all too big. They were all about Neptune-sized planets, so much too big to be Earth-like. And they were also very close to their stars. So it turns out that it's very hard to it's still very hard to see to find Earth-like planets, but these Neptune-sized planets turn out to be very common in the universe. And so overall, looking at the the mission results, because of this random alignment of planets and solar systems with respect to our line of sight, we're expecting to only see 1 to 2% of all the planets in Kepler's field of view. And Kepler found planetary planets and planet candidates around nearly 1% of its stars. So if you do the math, you divide 1% by 1%, that tells you what the percentage of stars are that actually have planets. And so that percentage is close to 100%, which is an amazing result because 25 years ago, we didn't even know of any planets around other stars. And now, after just a generation of looking, we've come to the conclusion that's supported by the evidence to say that there are planets that orbit nearly every star in the galaxy. And based on the statistics of Earth-sized planets that we have seen around these other stars, that the closest Earth-sized planet is within 20 light years. So 20 light years, to people who are familiar with science fiction, doesn't sound like very far. 20 light years, it's still a heck of a long ways because that's still on the order of about 100 trillion miles. So start walking. But it's encouraging that Kepler found all of these different planets that basically form a nice continuum. That we even found planets that there's no analogs to these planets in our solar system. So basically, if you start taking these planets and start sorting them into size bins, basically you find the number of Jupiter-sized planets, the number of planets that are smaller than Jupiter, and then you get to these two columns here, which are basically these super Earth-sized planets and these sort of mini Neptunes. And we're finding that these super Earth-sized planets and these mini Neptunes are the most common types of planets in the universe. And so that's very surprising. It's very encouraging that there are still these super Earth-sized planets, because even these super Earth-sized planets are planets that could have a lot of water on them. They could have, basically environments that are very friendly to the formation of life, and that they are very common in the universe. So there are lots of places for ET to grow up, and so for ET to start, evolving and learning, just like we did. And so, if you look at the overall history of exoplanets and exoplanet discovery, so there's nothing happening out here until about 1995, and we start finding planets in the 1s and 2s, and the Wobble Method was used primarily in the beginning because the technology was available. But then Kepler launched here in 2009, and you see the green here are the planets that are found with this transit method. And you see these massive surges that as Kepler collected more and more data, was able to find more and more planets. And so it was through the collection of years and years of data that allowed us to find these planets that are the appropriate distances from their stars to be habitable. And so that's why you get these sudden surges, is because the astronomers would take data for years and then release information about their planets and planetary candidates all at once. So you get times where you're looking at here about 1,000 planets being known, then suddenly a couple years later you're looking at twice that number. Is because the astronomers had these huge data sets that they're suddenly releasing, and we're suddenly understanding that there's a lot more planets in the universe. So 2009 was when the spacecraft launched. In that amount of time, things change. So kids grow up and get older, and spacecraft also suffer certain aging effects. And so one of those aging effects was that basically disabled the spacecraft in a way that forced us to move away from that single field of view that we were looking at, and forced us to basically look at different field of view every 90 days. And so even though the mission suffered this what would be considered a major failure, we were able to find a way of reworking the operations of the telescope so that we could observe these 10 degree by 10 degree fields of view for about 90 days at a time. And that if you look at small stars, you can still see planets that are in this Earth-like orbit around those smaller stars, because those Goldilocks zone around those smaller, dimmer stars are so much closer. And so we were able to look at all of these different fields of view And they're able to really open up the investigation of the telescope and the things that it looked at to all kinds of different areas. We were able to look at supernova, look at different areas of star formation, because there's a lot of other things that really benefit from this high sensitivity photometric measurements that we were making. And it's all these different areas. In fact, the Kepler areas of investigation really went across all areas of astronomy. You know, they looked at asteroids, we looked at planets, we looked at black holes, and so it really opened up the field of high sensitivity photometry to all sorts of astronomy, not just the astronomers that were interested in exoplanets. Now, I wanted to show this picture because this is basically Kepler's only snapshot, only picture of an Earth-like planet. So this image was taken in December of 2017, and the very Earth-like planet that we're looking at here is Earth. So this was a sort of a chance alignment of that new mission that we had, where the Earth was actually in our field of view. And so because Earth is very close, it's very bright. And so it basically creates this big column of saturation that you get, like when you point your camera at the sun, basically you get this big portion of the camera that's saturated. And so this is a picture of the Earth, you know, and if you look really close, really deep in there, you can probably see Colorado. But, you know, and we knew when this was happening, so we're all able to, members of the spacecraft team were all able to go outside when this image was being taken. So there are some photons being bounced off of my forehead that are going into this image. Probably not very many, but a few. But that was a nice sort of way that was a nice thing to do with the telescope. But as I said, the Kepler 2 mission that we took on after the end of the original mission really opened up all areas of astronomical inquiry. Unfortunately, last October, the spacecraft finally ran out of the propellant that it was using to help control its attitude. And so we finally got to the point where we could no longer point the spacecraft where we wanted to. And so we had to end the mission. And so officially in last October, November, we transmitted the goodnight sequence up to the spacecraft that basically shut all the systems down and just put it into a sort of a sleep state where the spacecraft is done. It's not going to be collecting any more data. It's not going to be sending any more data. So it was really a nice 9-year period that we were able to gather information and data from the telescope. But I'm reminded of the words of Master Yoda from the Star Wars. When he, I'm just paraphrasing here, and he says, rejoice for those spacecraft that become one with the Force. And so Kepler has become one with the Force, but the hunt for the exoplanets continue. There's a spacecraft called TESS, which was launched last year, which has 4 smaller telescopes, and what it's doing is instead of focusing on one area of the sky like Kepler did, it's looking across the entire sky, basically at the 200,000 brightest stars in the sky to look for exoplanets. In a few years, there'll be this observatory called the James Webb Space Telescope, and it'll be launched, and it'll be able to not only find exoplanets, but able to characterize those exoplanets and look at, well, what types of elements are in those planets' atmospheres. And then there's, you know, follow-on telescopes after that astronomers have planned, and they're in the initial stages of construction. So the exoplanet hunt continues. Even though Kepler may be gone, the search goes on, and, you know, we're pushing ever further into those components of that Drake equation, and they're further off to the right. You know, we know those fraction of stars that have planets, and we have some idea of those fraction of stars that have planets, that have Earth-like planets. And now we're going to start looking at, well, how many of those planets that are Earth-size could actually support life? And so that's where the science is being driven next. So that wraps up my presentation for tonight, and I'll take anybody's questions. So the question was, is there a cooperation between SETI and those planetary systems that we've seen? And the answer is yes. They have looked at some of those stars with planets that Kepler has found. The unfortunate thing is that for Kepler, we were looking at this one field of view, and most of the stars in our field of view were between 300 to 3,000 light years away. So it was a deep field of view, but 300 light years away is a long ways away in terms of the stars that SETI has looked at. So in order for a radio signal to make it across that distance, it has to be extraordinarily powerful. But there is a lot of cooperation between the exoplanet part of astronomy and the SETI Institute to follow up with observations of these planets, looking for any sort of signals that might be there. Yes.
So actually, one time I was watching TV about space,
Mm-hmm.
and actually, some people found a supermassive black hole,
Mm-hmm.
and they find that it's very interesting because black holes sometimes have this thing around them, but this things like you showed us a picture about Earth when it has a line.
Mm-hmm.
Usually it has a line.
Yeah.
And I find it interesting. I think the reason why it has no line is because actually black holes are made out of stars. And actually what happens to stars, I think actually how black holes are made is basically the star just keeps getting smaller and smaller, and then it just makes a big sort of explosion, but then it just makes a small thing, and black holes are like a planet, but except it sucks. So,
Well, one of the theories is that black holes come from stars, right? And that they are big, massive stars, and they basically collapse into a very small object. And the reason they have these things that are coming out the poles is because they're constantly pulling in dust and gas, and some of that dust and gas doesn't get sucked into the black hole, but it gets shot out along the axis that it's rotating around, right? So it gets shot out, and so that's what the astronomers are seeing from that jet. This is something that's very different because the Earth is so bright. Some of the part of the camera that is seeing the Earth is getting so much light that light is actually bleeding out into other parts of the camera. And so it bleeds out into other parts of the camera that basically form this giant column like that. And so that's the reason why you see that column. It's from the fact that the Earth is so bright in this picture. Other questions? Yes?
You said in 2014 there was a failure with Kepler,
Uh-huh.
which then made it have to go into K2.
Right.
What was the failure?
So the failure was that, I showed that spacecraft component, the reaction wheel. I talked about how inside of that housing there was a flywheel. And so in order to control a spacecraft's attitude, you need 3 of those, because there are 3 ways that an object can rotate. It can rotate like this, it can rotate like this, and it can rotate around like this. And so you need 3 of these wheels to control the spacecraft's orientation. Well, it was in July of 2012, we lost one of the reaction wheels. And in May of 2013, we lost a second reaction wheel. So basically, we were down to 2 reaction wheels because we started with 4. And so the common knowledge is that you shouldn't be able to control a spacecraft with just 2 reaction wheels. We found this novel way of orienting the spacecraft so that you could use pressure from the sun to help balance that 3rd axis. But that necessitated us to basically, instead of looking at a set of stars that are very high in the northern sky, it required us to tip the spacecraft over, close to 90 degrees to basically look at star fields in the plane of the Earth's orbit. And so in that scenario, so if the spacecraft is moving around, in an orbit like this, we're basically pointed in a constant direction, and there's only so far you can move the telescope in this direction because light would start getting down the barrel of the telescope, and in this direction you're limited by how much power you need the solar rays to generate. And so that's what kept us from basically looking at the same star field all the time. But if you move a certain amount, if you move by 90 degrees, every 90 days, then you can cover a bunch of these different areas of the sky. Yes?
Did those components fail prematurely, or is that about their lifetime you expected?
Well, the question was, did those components fail prematurely? And the desire was to have those components operate for at least 5 years. And so the first one failed after about 3 years. And luckily, the second one didn't fail until just after the 4th anniversary of the launch. So we were able to collect the 4 years worth of data that was the original mission. But yes, they did fail what we would think of as prematurely. Now the other 2 wheels, they operated for 9 years without any problem. So obviously there are some wheels that were good and some wheels that were bad. But the actual failure mechanism that was finally identified just a few years ago for why those wheels failed was because in July of 2012 there was an explosion on the sun called a coronal mass ejection, and it sent all these high energy, high velocity particles out into space, and Kepler was inside of that cloud of particles that got sent out. And so what happened then was all these wheels are inside of their houses, and they're spinning, and some of them there was like an electrical discharge inside of the housing, and that caused like a micro fracture in some of the ball bearings. And basically over time that micro fractures got bigger and bigger to the point where the electric motors that were used to turn those flywheels didn't have enough torque to overcome that friction. So, some down-to-earth problems, ball bearings, right, failing.
So our own star turned out.
So, any other questions?
I have a really silly question here.
Okay.
Not related to the class. How many current performance followers space employees do we have?